In this video, we're going to go over the combined gas law, which, surprise, is just the law that you get when you combine the laws that we talked about from the last video. The important thing when using this is that you've got to make sure that your temperature is in Kelvin, because Kelvin is an absolute scale, which means the zero is actually like the true 0 point of temperature. You can't go lower than 0 Kelvin. That's the point at which all movement of particles stops. So when we talk about like 0 degrees Celsius, it's just an arbitrary kind of 0 point where water freezes, which really doesn't have a whole lot of meaning. So when you talk about the combined gas laws, just make sure that you're always converting temperature to Kelvin. Here are the equations to go back and forth from Kelvin to Celsius and Celsius to Kelvin. So make sure you have those. One way to remember this is that Kelvin, the 0, like I mentioned, is the true 0. It can't go negative. You can't have a negative Kelvin. So because Kelvin can't be negative, you always add to get to Kelvin. So just think Kelvin's always positive, add to get to Kelvin. Celsius can be negative, subtract to get to Celsius. That's how I remember it. And then when you combine those gas laws that we talked about in the last video, this is the equation you get. What this is useful for is if we have the conditions of like a balloon. We know its pressure, its volume, and its temperature. And let's say we increase the pressure on the balloon, we decrease the temperature on the balloon. We can calculate its new volume. So if we know its initial conditions and we change 2 of the conditions or 1 or 2 of these conditions, we can calculate the third one on this side. So that's what it's useful for. We'll do a couple examples with this. Another way to look at this is if you cross multiply here, so the T2 multiplies up to here, this T1 multiplies up to here, you can rearrange this to get this equation. The people tend to like this equation better because the algebra is a little bit easier coming out of this. Usually, well, you always know 5 of the 6, which means, let me get my pen out here. If I know 5 of the 6 of these variables, usually you just isolate the one you don't know, and then the other 2 just get divided out to this side. Versus when you use this equation, if you don't know like T2, the algebra to get T2 by itself is a little bit trickier, right? You got to like multiply T2 to this side, multiply T1 to this side, divide these down. The crisscrossing of algebra to get some of these variables by themselves is a little bit more cumbersome. So this equation tends to be more algebra friendly. But the warning that I will give when you use this equation is this trips everyone up. Well, not everyone, but a lot of students up. It's P1, T1, T2. It's so easy to just get into a groove and just put P1 or P1, V1, T1, P2, V2, T2. You will get the wrong answer if you do that. So just make sure that you put your T2 on this side, your T1 on this side when you set up this equation. So let's go ahead and use this. So example question here. A helium balloon has a volume of 50 liters at 25 degrees Celsius and 820 millimeters of mercury for pressure. What volume will it occupy at 650 milliliters of mercury and 10 degrees Celsius? So the first thing we're going to want to do is convert these to Kelvin. So we just take the, I guess I got the wrong equation there. We'll just flip that around. The Kelvin goes to this side, Celsius goes to this side, and we're going to add. Perfect. Problem solved. So we take 25 degrees Celsius, we add 273, and we're going to get 298 Kelvin. I'm not going to worry about the 0.5 just for the sake of getting through this video a little quicker. If we add 273 to this, we get 283 Kelvin. So there we go. We've got our temperature in Kelvin. The other thing that's important is your pressure and your volumes have to be consistent. So like the 2 pressures, doesn't really matter what units they're in as long as they're consistent. So let's check. This pressure is in millimeters of mercury. This one is 2. Our volume, we only have 1 volume, and it's in liters. So when we solve this, the volume that we calculate is also going to be in liters because the pressure and the volumes have to be consistent, and you'll see how that works out here in a second. So it says it has an initial volume of 50 liters. So we're going to go ahead and fill this out, 50 liters. The initial temperature is 298 Kelvin. When you do Kelvin, it's not degrees Kelvin, it's just Kelvin. There's no degree symbol for Kelvin. The initial pressure was 820 millimeters of mercury. It says the pressure changed to 650 millimeters of mercury. The temperature changed to 283 Kelvin. And it says what volume will it be? So there we go. This, I think, is the hardest part, is trying to read this question and figure out what's your initial conditions, what's your final conditions, what is it asking for. So now we're going to plug this in. I like to put everything in parentheses. That just helps me kind of keep things organized. Millimeters of mercury times the volume, which is 50 liters. T2, not T1, so I go down here and put 283. 283 Kelvin equals P2, 650 millimeters of mercury. Then from there, V2 is our question mark. So I'm just going to leave, if I don't know it, I just like to write it down as the variable that it is. And then T1, so don't forget that T1 is 298 Kelvin. Whoa, there we go, 298 Kelvin. So here's where we got to do a little bit of algebra now. We need to get V2 by itself. These two numbers are multiplying by V2, so what we're going to do is divide both sides by that. So I would divide this side by itself. If I divide this side by 650 and 298, I'm going to do the same thing to this side. 650 millimeters of mercury, 298 Kelvin. So then this is no longer there. So now V2 equals all of this. And that's how every one of these problems is going to go. Whichever side your variable is on, or your unknown, you just take the numbers that are beside it, or on the same side as it, divide it to the other side. Now you'll notice millimeters of mercury divided by itself cancels out. That's why our pressures have to be consistent. Temperature has to be in Kelvin. Most common mistake is that people leave it in degrees Celsius. You will definitely get a wrong answer if you do that. So now we take 820, I got to pull my calculator out here, 820 times 50 times 283 divided by 650 divided by, whoops, I hit multiply, divided by 298. And we end up getting 2. Let me check my sig figs here real quick. We got 3, 2, 3, 2. So 2 sig figs, 2.2. We'll round it to 2.2 then. I got 2.18 and then some other stuff. We'll just round it to 2.2. So we know that the new volume of this balloon will be 2.2 liters. So it went way down, which kind of makes sense here. Our temperature decreased. We know that volume decreases with temperature. Our pressure did decrease, which means that should make our volume go up, but the temperature seems to do more there for us. Actually, something seems wrong on this. Did I type something in wrong? It seems like a low value. I'll recheck that later. Calculate it yourself if you get something different than me. Or if you find the mistake, point it out when you get to class and let me know. So let's do another one here. Helium-filled balloon has a volume of 50 liters. So the initial volume, 50 liters, 45 degrees Celsius. Let's just convert that, add 273. So we're going to put that in as T1. We've got 318 Kelvin. So just make a habit of that. 1.5 atmospheres. 1.50 atmospheres. What temperature? So it's asking me what temperature is it going to change to at 2.5 atmospheres. So the pressure's going up and the volume is going down. So we solve for this just like we did last time. We put these in here. ATM, that's our P1. V1, 50 liters. And then remember T2, which we don't know, so we put in T2. Then we go V2, which is 20 liters, 20.0 liters, times P2, 2.5 atmospheres. And then T1, which is 318 Kelvin. Okay, so here's my unknown. So again, you take these and you just divide them over to here. So we've got 1.50 atmospheres. Oh, not sure what happened there. And we take our 50 liters, bring it down. Oh, that's what's happening. I accidentally clicked the button on my pen, making it upset here at me. So we've got 20 times 2.5 times 318 equals, then I'm going to divide that by 1.5, divide by 50, and I end up getting 212 Kelvin. I should check my sig figs. Technically this has 2 sig figs, so we should round this to 210 Kelvin, so that it rounds down from 212. And then if you want, you can subtract 273 from that. Actually, I got to do 210 minus 273. So that would be negative 63 degrees Celsius. So you get reported in either way. It didn't specify what you needed, so we'll put it as both. Go ahead, you can take a look at this one. There is one thing I want to actually mention on this one before I leave this video. It says if the temperature is constant. That's really useful to me, because if my temperature doesn't change, I'm going to end up dividing the same temperature by itself and they'll cancel out. So the nice thing, if any of the variables are held constant, that means you just get to take them out. Don't even put them in. So then this equation becomes P1 V1 equals P2 V2. You can ignore the temperatures. If temperature is held constant, you get to take it out. The same thing is true. Let's say they tell you pressure is constant. Then you'd simplify this equation to V1 T2 equals V2 T1. So you get to do that. So if they say pressure is constant, you just get to take the P's out. If volume's constant, you get to take the V's out. In this case, temperature is constant, so then you get to use this equation. So you can just go ahead and cross these out here too. We don't need them. And go ahead and see if you can solve this one on your own. And then I believe there's one more, but we're running out of time. They're the same thing as the first two. So I'll leave you to that, and then we're going to start talking about the ideal gas law in the next video.